So, starting into chapter 13, 13.1. Chapter 13 is a pretty, it's a pretty long chapter too. I think there are 10 sections that we talk about. So functions of several variables. So our notation, what we're going to do today is mainly kind of like we started out chapter 12. We're going to talk about how we visualize these functions. Our notation for multivariable functions, we're going to write z equals f of xy, or this would be a function of two variables, or we can say w equals f of xyz, etc. So this is going to be our notation. Yes.
So are we done with vectors?
Just briefly.
Yes.
Tranya, we've had a little taste of the Tranya. We're going to let it. We're going to let our palate develop, and then we're going to come back to the Tranya a little later in chapter 13. And in chapter 13, it's nice because we get to learn several new map symbols that we've never used before, which is always fun. All right, so we have used multivariable functions in the past. We've used them for a long time. So examples of a multivariable function. Just some easy examples. We said our work is the force times distance. So work is a multivariable function. It's a function of force and distance. Area is length times height. Multivariable function. Volume is for a rectangular solid, length times width times height. So volume is a three-variable function. So we've worked with these kinds of functions before. We're going to go into a little more detail in this chapter. So we call f. So if we have f of xy, f of xyz, f is a function of x and y, or xyz, and our set xy or xyz is the domain. And our range is just the range of possible values, just like a single variable function. We can combine multivariable functions just like we combine single variable functions. So just quickly. Just a reminder on combining functions, if we have f plus or minus g, so both of these are multivariable functions of xy. So we're talking about a two-variable function here. This is just going to be f plus g. F times g of xy is just f of xy times g of xy. So we're combining them just like single variable functions. We can do a quotient, and this should be xy. And this is just f over g. And we don't want g not equal to 0. G's not equal to 0. And we can do a composition, g of h is g of h of xy. And looking at this composition, what do we need? What do we know about g here if we're doing this composition? What do we get out of h of xy? And we just get a number. We get one number. So g has to be a function of a single variable. So h of xy is just, we just get a, plug in x and y, we get a single number. So g has to be a function of a single variable to inform this composition. And we'll talk about compositions a little later. So just a reminder about how we can combine, these multivariable functions combine just like single variable functions. What we're interested in this section is visualizing. How do we visualize these functions? Because it helps to know what they look like. So we want some tools for visualizing these functions, just like we had some tools for visualizing vector valued functions, when we talked about surfaces in 3 dimensions. We wanted some tools to be able to visualize them. So I want to do a couple of examples, and then we'll talk about a couple of other ways that we visualize these functions. So for this first one, we want to sketch a graph of this function. F of xy equals xy for x greater than or equal to 0, y greater than or equal to 0, and 0 elsewhere. So our domain of this function, looking at our definition of the function, what's the domain of this function going to be? We're defining it as xy for x greater than 0, y greater than 0. So where are we getting our input values? Positive values of x and y. So we're talking about the xy plane in the first octant. So we can say our domain is the positive xy plane. So that's what this is telling us. X is greater than 0, y is greater than 0. And our range, so what possible values can the output of this thing have? If x is greater than 0, y is greater than 0, and we get xy and a 0 everywhere else. Positive values of z. So z is going to be, and it could be 0. Z is going to be greater than or equal to 0. So that helps us a little bit. So here's our coordinate axes, and I'm going to draw it turned a little bit just to help us visualize. All right. So to visualize this function, we're going to pick a z value. We're going to pick z equals 25 and try to so that we're going to cut off our inputs that only give us z equals 25. So I'm going to go out here to x equals 5, and I'm going to go over here to z or y equals 5. And right above this point, 5, 5, where so there's my point 55 in the xy plane. Z is going to be what at that value? 25. So we're going to get a point way up here. So here's z equals 25. And then if we look at this, what this surface is projected onto the xy plane, we have x equals 25 over y. what kind of graph is that in the xy plane? Or xy equals 25. What is it? That's perfect. So Jacob did this. So it's a hyperbola. So if we project this onto the xy plane, we get a hyperbola, and if we project it, we could also say that y equals 25 over x. So it's going to have some kind of hyperbolic shape. So what's going to happen here is we get this from here down to 0, 0. We get kind of a hyperbolic shape, and our graph is going to go down here to the x and y axis because it's 0 everywhere except in the positive, above the positive xy plane. So the way I visualize this one is like a sheet of fabric that's fastened to the x and y axis, and you're taking the corner of the sheet of fabric and kind of picking it up. So almost like you're like a tent. So it's staked down on the axes, and you're picking up that corner. So let's look at a better drawing of this surface. So there's our xy plane looking down. Our function is 0 along each axis, and then we're picking up this corner here. So that would be our surface. That would be a picture of that surface. And if we look at it edge on, we kind of see this slightly hyperbolic shape to the surface. So there's one way of visualizing the surface is picking a point and seeing what's going on with your values and what the z values are going to do. And we'll get better with this as we go on. All right, questions so far. And as we do this, we'll get better at it, and we'll talk about some other tools that we will use to visualize these surfaces. All right, next I want to ask you guys some questions about how these surfaces might behave, and then we will talk about another way to visualize it. So if we had a graph, or a function, and we have g of xy is f of xy minus 3. How would these, if we graph these two, how would their graphs compare? One would be shifted down 3 units. So we're just shifting this down 3 units. How about if we had g of xy equals 1/2 f of xy? How are these two graphs going to compare? What do we think that 1/2 is going to do to the graph of this function? Shrink it. So it's going to compress it. How about g of xy is negative f of xy? It's going to reflect it over the, in this case, where would we reflect? We're in 3 dimensions.
Y.
So the z turns negative, so we're reflecting it over the xy plane. All right. So just intuitively, they behave. These graphs of these functions behave like functions of a single variable. We just have that added dimension. All right. Next thing I want to talk about is contour maps, level curves, and level surfaces. So another tool that we can use to visualize these surfaces, to visualize these graphs of these multivariable functions, are what we call contour maps or level curves, contour lines, level surfaces. So what we do is we sketch curves where f of xy equals a constant. To get an idea of what the curve looks like. Anybody think of an example of something, some kind of thing that we use on a fairly regular basis, where we're looking at curves where some multivariable function equals a constant? So a couple of examples that I think of are weather maps. So when you see a weather map, you get the shapes where the pressure is constant, the isobars, the same pressure. So you get those, the weather maps have all the curves sketched on them. So that would be a contour map. They're sketching out where the pressure is constant. So you get an idea of how the pressure is behaving. If we think of pressure as the z value, we get an idea of how the pressure is behaving. Another example would be a topographical map. So on a topographical map, your curves are where the elevation is constant. So your curves, they have all the curves on, and from looking at the topographical map, you get an idea of what the terrain looks like. So that would be another example. For physics people, an example would be where you sketch equipotential lines, equipotential fields. So if we have an electric field or a magnetic field, we sketch where the potential is constant. And that gives us an idea of how the field is behaving. So what we're looking for our contour lines, contour maps, level surfaces, is if the contour lines, if the curves are far apart, we call these curves contour lines. If they're far apart, that means f of xy is changing slowly. So as we move from one contour line to another on the plane, if those contour lines are far apart, that means our surface is changing slowly. So the distance between the change is very small. If the contour lines are close together, then our surface z is changing more rapidly. And when we, what we usually do when we sketch these contour lines is we pick these constants so that the constants are equally spaced. So we pick our constant 1, 2, 3, 4, and that gives us a better idea of what our surface looks like. If we have a function of more than one variable, we would not get level curves. We would get level surfaces. So then our surface, we're thinking of our function, if we have a more than two variable function, it's describing, we could think of it as describing a four-dimensional surface, and our level curves are actually three-dimensional surfaces. So we get level surfaces. So I want to look at a couple of examples of what a surface looks like, what a contour map looks like, what the contour lines look like. So for these next examples, we want to match the graph with its contour map, with its level curves. So we're looking at where the curves tell us where the function is contour. So let's look at these. So we want, for these, we want to match the surface, the function, and it's the graph of the surface with its level curves, with its contour map. So for this first one, we have f of xy equals e to the 1 minus x squared minus y squared. So here, our function out in this part of the plane, the function is changing very slowly. So our contour lines should be very far apart. And as we get closer to the origin, our function is changing more rapidly. So our contour lines should be closer together. And this shape looks kind of circular. So this would have to match C. And how about number 46? We have this hyperbolic paraboloid. So this is as we move away from the origin this way, our function is changing less rapidly, and as we go here, our function is changing very rapidly. So that's going to match D. And this is e to the 1 minus x squared plus y squared. How about number 47? We have this kind of strange surface with this bump in the middle. That's going to have to be B. So we get these parabolas. And then finally, and that's the natural log of the absolute value of y minus x squared. And finally, 48, we get cosine of x squared plus 2y squared over 4. We get, these are ellipses, so our contour lines are elliptical. Now let me show you how we would go about figuring out if we didn't have a picture of our surface, we didn't have a picture of these surfaces, how we figure this out analytically. What do the contour lines look like? What are the level curves? So for number 45, we want e to the 1 minus x squared minus y squared equals a constant. And we want to figure out what these contour lines are going to be. So we want to get an equation for, guys, relax. We want to get an equation for what these contour lines, an equation in terms of x and y, what these contour lines are going to look like. So we set our function equal to a constant. Now I'm going to take the natural log of both sides. So I get 1 minus x squared minus y squared equals the natural log of c. Well, the natural log of c is just a constant. solve this for x squared and for x and y, I get x squared plus y squared equals 1 minus the natural log of c. And the natural log of c is just another constant. So I get x squared plus y squared equals, I'm just going to call it c1. X squared plus y squared equals a constant. And those are circles. So that's how we would figure out that those contour lines, those level curves, were circles. So if we were given this function, we could figure out that the contour lines were circles, and we could sketch a contour line by plugging in several values for the constant and sketching those circles. For number 46, we have e to the 1 minus x squared plus y squared equals a constant. Same process. We have 1 minus x squared plus y squared equals the natural log of c, some other constant. And I can write this as x squared minus y squared equals 1 minus the natural log of c, which is just another constant. So x squared minus y squared equals some constant. And these are hyperbolas. So the level curves of this function would be hyperbolas, and we'd be able to sketch those hyperbolas. And that's how we figure out that these are the level curves. For number 47, set this function equal to a constant. Natural log of y minus x squared equals a constant. So we exponentiate both sides. So y minus x squared, absolute value of y minus x squared equals e to the c, which is another constant. And we get y equals x squared plus some constant. And that tells us that the level curves of this function should be parabolas. And I guess since we have the absolute value, we'd get a plus or minus there. So if I took away the absolute values here, this would be a plus or minus, and we have a plus or minus a constant to get our parabolas. And then 48, to get our ellipses out of here, we have the cosine of x squared plus 2y squared over 4 equals a constant. So x squared plus 2y squared over 4 is the inverse cosine of a constant, which is another constant. And we get x squared over 4 plus y squared over 2 equals some constant. And there are our ellipses. So that's how we would decide, if we didn't have our graph, that the level curves of this function are elliptical. And we could sketch those out. And we would get a picture that would look like this. And let's look in your book, in your online textbook. If you go to your online textbook, they have an interactive three-dimensional graphs for a lot of these homework problems. So you can look in your, if you look in your online, the online book, they have graphs of these. I have some pictures, some graphs that I made of these other surfaces, so we get a better idea of what they look like. So there was the first one. There's the e to the 1 minus x squared minus y squared surface. So if we look above here, our level curves would be all around this kind of circular shape. And we get this exponential function that goes up towards the origin, towards the z-axis. There's our hyperbolic paraboloid. And if we look here, there's our parabola. We turn it this way, another parabola, and there are our hyperbolas. There's that natural log of absolute value of y minus x squared. So all along here, the function gets very, very, very small. Kind of an interesting surface. And then the cosine one. So we get these ellipses, but then we get that cosine, the periodic function going on with the cosine as well. That one's kind of a nice one. All right, questions on that part? All right, so let's do a couple of these on our own. So what if we had f of x, y is x squared plus y squared, and we wanted to sketch the level curves. So we're going to set f of x, y equals a constant, and I wanted not x squared plus y squared, I want x squared plus 2y squared. So we have x squared plus 2y squared equals a constant. So what are our level curves going to be? Ellipses. So we get ellipses. And to sketch our level curves, we set our constant equal to various values. So if we said x squared plus 2y squared equals 2, we would get x squared over 2 plus y squared equals 1. We could set x squared plus 2y squared equals 4. That would give us x squared over 4 plus y squared over 2 equals 1. So those would be our level curves. And if we sketch those out, we end up with our level curves being these ellipses in the xy plane. Something like that, if we sketched out several of them. What would this surface be? Z equals x squared plus 2y squared. What do we think that surface is going to be? These are our level curves. This is telling us where Z is, how Z is changing. So where the level curves are far apart, Z is changing slowly. Where they're close together, Z is changing rapidly. Kind of like a bowl, right? Here where they're closer together, it's steep. Here where they're far apart, it's not as steep. Is the bowl both side up or both side down? Soup in or soup out, right? We can't tell just from the level curves, can we? What does the function tell us? When x and y equals 0, z equals 0. So is it gonna hold our soup or is it gonna spill our soup? It's gonna hold it, because down here where z equals 0 is the very bottom of the bowl. So let's look at a picture of this one. There's our bowl. Ellipses for our level curves. Z equals 0 down here at the bottom, and then it goes up. Hold a lot of soup. How far did I go? Z goes up to 10 here.
Yeah, probably.
You'd have to hold it up there. Or you could be like the physicist with the ball bearing and come up with interesting ideas about
Right.
friction.
Right.
Um,
Oh, it's yeah, let's try the question.
all right, let's see. Let's do, since we're running a little short on time here, I want to ask you a couple of questions. Before we finish. If the level curves of z equals f of xy are circles, then the graph is a hemisphere. So if we have level curves that are circles, the same that our graph has to look like half of a globe. False. And why would that be false? The cosine one that was elliptical, but we could make it circular if we took the 2 away from the y squared. So, and we also looked at the graph. We said f of xy equals e to the 1 minus x squared minus y squared. The level curves of that were circles. So just because we have circles for level curves doesn't necessarily mean we have a hemisphere. Next 2 questions. What would this surface look like? What could it look like? Our level curves are hyperbolas. Yeah, the saddle shape. The saddle shape. So it goes up this way, but down this way. So this could be a saddle shape, or it could also be kind of a plateau, right? And it's going down on 4 sides. So it could be a saddle shape. It could be kind of a plateau. So this could be a hyperbolic paraboloid. It could be like a plateau. So this could be the highest point, and we could be going downhill everywhere else. And these could be kind of ridges. How about this shape? What could that one be? Yeah, we just looked at one like that. This could be a top half of an ellipsoid, so a bowl shape. An upside down bowl, so it could be up or down. And did I have pictures of these? Let me see. Oh, no, that was a different one. Oh, that's the last one. Okay. All right, one more question. So here's our weather map. These are isobars. And the question asks us, we have some points listed. We want to know which point is at the highest pressure, which point is the lowest pressure, and the wind speed is the greatest where the isobars are closer together. So which point is going to have the highest wind speed? B is going to have the highest wind speed because the isobars are close together there. And when I was a kid, I always thought of the wind going downhill. Where the bars are close together, it's kind of going downhill, so the wind is going downhill. So which point is the highest pressure? Can you read the numbers? C, this is 1028, 1032, 1038, and here we're going 1024, 1020, 1016, 1012. So the pressure is going down here and it's going up there. So point C would be the highest pressure. All right. Homework.
I know, but based on the map, it looks like Denton is going to have very little wind this time around. I mean, we dodged a bullet there.
Dodge the bullet. You went running last night? It was really nice.
All right, there you
I mean,
go.
that's a lot of homework.